About how we're going to use this logical reasoning in class here. We're going to use it as, or we're going to begin to introduce it as algebraic proofs. Okay, so what I want to do is I want to kind of talk through this process of how you go through the logical sequencing of a formal proof. Okay, so here's an example of a proof that's all set up. It has an initial state, a given statement. It has an end state, a state that you're asked to prove. And then it's set up in these two columns, a column for your statements and a column for your reasons. And anytime you begin a two-column proof, you always start with your initial state. So all you're going to do is you're going to copy the initial statement word for word. So 3x plus 5 is equal to 5x plus 17. Even if it's a phrase or a sentence, that is the statement that's given, you're always simply going to copy it word for word. Don't make any translations, don't interpret it, just copy it down. Right? And your first justification is always going to be it was provided as given. And so given is always going to be your first reason. So when you guys do proofs, the way that proofs are going to be or show up on the assessments. Okay, so for quizzes and tests and even the final, it's all going to be multiple choice or kind of a drop-down matching type of thing. So what you'll need to do is I will usually give you a statement, and you need to just be able to find what the actual justification is for that statement. Okay. All right, so from this, once we begin our initial, or once we rewrite our initial state, okay, and I use algebraic proofs because you guys should be very comfortable working through the steps of solving simple algebraic equations. So what would be a next possible step for solving this equation and turning it into the end state that we're looking for? What would be one thing that we can do? As you go through these, you want to do one step at a time. Olivia? Okay, so if you move your x's so that they're on the same side, you would get the new statement 5 is equal to 2x plus 17. And so the reason for that is just the justification that's used. It's a mathematical axiom. We subtracted the same value from both sides, so we call that subtraction property. Notice how I abbreviated this. Okay, often in these reasons you can abbreviate the justifications to make it simpler or more efficient to write. Okay, so if this is what my second step was, what would my third step be? Jen? Okay, so now if we move the constants over to the same side, we get negative 12 is equal to 2x. Right? And so once again, we use subtraction property. So because we use the same justification, and statement 3 did not have to build upon statement 2, it could have been derived immediately from statement 1. We could have combined these two in the same step, and I'll show you that here in just a second when I do an alternate form of this. Okay, but subtraction property again justifies this step. What would be the next step in this? We divide both sides by 2. We get the new statement negative 6 is equal to x. Again, any mathematical operation becomes an axiom. Okay, so division property is a justification that applies beyond just the scope of geometry, so it's an axiom. Okay, now, is our end state exactly the same as what we're asked to prove? It's the same idea, but is it written exactly the same? No. If we had been going through this proof right here, we'd be done in step 4. However, in this example, I wanted it set x is equal to negative 6. Does anybody remember what allows you to rewrite statement 4 just by flipping those terms? So you get x is equal to negative 6. Anybody remember what that was called? What axiom that was? So the reflexive one itself is that just x is equal to x. Something is equal to itself. And now I'm going to show you here on this alternate one how you can use reflexive to show this. Or actually, let me go through that here. So if we wanted to use reflexive property, to eventually get to this step, what we would need to do is we would need to introduce x is equal to itself. Okay, so we know that now x is equal to itself. What would then allow us to take this statement from step 5? What could I replace this x with? What's x equivalent to? -6. So this is a case where I have two things equal to the same thing. So -6 is equal to x and x is equal to x. If two things are equal to the same thing, they're equal to each other. Does anybody remember what that's called? What property is that? That's an example of transitive property. Or I could have also simply taken statement 5, and what can I replace, just directly replace this x with? A -6, and so I could have also called this substitution. Anytime you directly replace something, it's an example of substitution. So I could have gone through these 6 steps to come up with the proof in this form. Now, here's the thing. Step 5 and 6 can be combined into one step, and it's the other axiom that allows you just to switch it around, and that is the symmetric property. Okay, so let me show you the efficient way to go through this proof. So I'm going to redo it. I'm just going to reorder the terms here slightly. So step 1, copy what you have exactly word for word. Justify it as the given state. It's the initial given state, so the justification is given. Okay, step 2, what I can do here is I can, since subtraction property works for both of these first initial steps, I can do that together all at once. Okay, so let's say I subtracted a 5x from both sides. At the same time, I move my constants to the other side and subtracted a 5 from both sides. Because that's all one specific property, I can combine it into one statement, and I get -2x is equal to +12. I can then isolate my x by dividing both sides by -2, so I get x is equal to -6. That would be division property. And then my final step, if this is how I chose to approach it, is I need to reorder these in order to get the end state exactly as it's written with the -6 first. So I could have jumped directly to this statement by using the symmetric property. Okay, so I wanted to show you that these can be done multiple ways. It doesn't all have to be done the same way that maybe I show you. It doesn't even need to take the same number of steps I show you. However, when I give you a proof, I'll often tell you exactly how many statements there are in it. And when I give you that number, it doesn't mean that you can't do it a different way. All it means is that's the most efficient way that you can approach that problem. Okay, so if it happens to be the most efficient way, you can approach it. Okay, but if you need more steps, then you might wind up using more, and that's okay. It doesn't have to be specifically one process. All right. So I want you to go ahead and try the second one on your own. So my first step, I'm just going to repeat my given initial state, and I'm going to justify it as being the given information. So that's always going to be consistent. And so what's a possible second step here? What can I do to both sides, Josephine? Okay, so if I add 17 to both sides, I get -5x plus 10 is equal to 5x. Justify it by explaining the process. The process was addition property. I added the same thing to each side of that equation. Okay, and so what would be my next potential step in 3 here, Sydney?
I don't have to be in the same order.
No.
And the next step is I would subtract 5x from one side.
Okay, so if we move the 5x over, so I'm going to add it to both sides of this equation. That gives me 10 is equal to 10x. Now, I could have combined that in the same step. because it's the addition property for both of those. And so my final step here, as far as getting x to be completely alone, is just like the last one, divide both sides by 10. It's an example of division property. And so my end state is not exactly what I'm asked to prove. It's almost there. There's just one quick little adjustment, and that is to switch the order. And you can switch order by using symmetric property. Okay, so this would be one possible answer. Now, some of you might have combined steps 2 and 3. Some of you might have written step 3 above step 2. It's fine. There's no set order that has to be done. And we could have even gone through the reflexive property and substitution or transitive property like we did in the last example. Okay. All right, if you were solving this in the most efficient way possible, okay, if I vary it slightly by reordering the terms here, the most efficient approach to this would be to take step 2. I want to get my x's alone on the right, so I'm going to add a 5x. I'm going to put all my x's to the right. So that gives me a 10x over here. At the same time, because I'm using addition for both of these modifications, I can combine them in the same step. If I add 17 to both sides, I get 10 is equal to 10x. That's addition property. I can then find my end state, divide both sides by a 10. So division property justifies this. So I could have answered this in 3 steps. That would be the most efficient or minimal number of steps that it would require. However, both of these would be correct. It doesn't matter if you have extra steps, as long as they're justified, you're okay. All right, questions about that, the examples of formal proofs? We're going to start with algebra. Eventually, in the next section and for the rest of this chapter, we will also begin using proofs with geometric relationships and not just the algebra.